Hello everyone, and welcome back to some more remote learning. Today we're going to go over continuity. So what exactly is continuity? And maybe you've heard it mentioned before back in your algebra or geometry classes. So what exactly does it mean for a function to be continuous? Well, we often describe it as a function that does not have holes or jumps, essentially no breaks. So let's talk about that, and then we'll dive into what creates those holes, jumps, or breaks so that we have more of a formal definition. So if you look what I've graphed below, I have three continuous functions. And one thing I like to think about is drawing this function. Where you start drawing, can you draw that without lifting your pen or pencil off the paper? Obviously, a straight line with no holes, we can. A polynomial function. I was able to start and stop without lifting up my pen. And then also here's a trig function where there are no holes and breaks as I trace along this. So each of these three functions is continuous. And again, that's because there were no holes or jumps, essentially no breaks. But that isn't exactly very technical. So let's go ahead and go over the definition of continuity. Let's take a look at what makes a function continuous. So f is continuous if all of the following are met. So there's three different things we're going to look at in order for a function to be continuous. If our function does not meet one or more of the criteria, we say it's not continuous. It has to meet every single one of the following criteria. Our first is that f of a is defined. So if we have some x value that's represented by that variable a, then we do indeed have f of a somewhere. So that's one thing we can check for. Another thing is that the limit of f of x as x approaches a exists. So what has to happen in order for a limit to exist? Coming from the left and coming from the right, both left side and right side limits need to be that same value. And remember, as we go towards infinity for a limit, or as we go towards negative infinity, technically those do not exist. And then lastly, we're going to tie these two together. The limit of f of x as x approaches a equals f of a. So what we're saying here is that the value of the function at that point a is equivalent to the limit of f of x as x approaches a. Now, like I stated before, all of these need to hold true. If there's some point A where one of these three has failed, then that is a point of discontinuity, a point where our function is not continuous. So as we move on to example 1, we're going to state any points of discontinuity, but we're also going to state why. I think this is helpful for really driving home the concept of a function being continuous. So if f of a isn't defined, we're going to say that it's discontinuous because of that. If the limit doesn't exist, we're going to state that. So we're going to look at these three conditions for a function being continuous and see which fails. So looking at a, we can see our function. If you can envision dragging your pencil along and then all of a sudden you get to this point here and you have to lift it up, and then right after that point, continue drawing again. Here is our point of discontinuity. We have a point of discontinuity at x equals 2. So x equals 2 is our point of discontinuity. But why is that a point of discontinuity? Let's look at back up those conditions. It fails this first one right here. F of a is not defined. There is no f of a that's defined for this function. There is no f of 2. When we get to the x value of 2, we don't know its value. So right away, it fails that first condition. So we're going to say that f of a is not defined, or f of 2 is not defined. And while we're at it, let's see if it meets the other conditions. We know it's not continuous because it fails that first condition, but let's look at this next. Does the limit exist? Yeah. Coming from the left towards a and coming from the right towards that value of 2, the limit exists. But here we go, we fail 3 again because the limit does not equal what f of a is, because f of a is undefined. So I'm also going to write that the limit of f of x as x approaches 2 does not equal f of 2. And because f of 2 isn't defined, obviously this third statement is not going to be true. In part A, we failed 2 of the above conditions, but we only need to fail 1 for it not to be continuous. Now looking at part B, you can see here, I'm drawing my line, drawing my line, drawing my line. Whoop, here's a jump. Now I have to move my pen or pencil down to the bottom of the page and continue drawing. Right away, where that jump occurred, that's our point of discontinuity, which again is at an x value of 2. But why does it fail in this case? Well, let's look at the first part. F of a is defined. Yeah, it sure is. When we're at 2 in the x, we're at 4 in the y, or 4 for f of x. That is indeed defined. But here we go. Does that limit exist? Coming from the left and coming from the right as x approaches 2, do we have that same finite value? Coming from the left, we're going towards 4. Coming from the right, we're going towards, it looks to be about 1, maybe a little over 1, maybe 1.5. But regardless, that limit does not exist. So it fails condition 2, and because that limit doesn't exist, it also fails that third condition. So I'm going to say that the limit of f of x as x approaches 2 does not exist. That's why it's discontinuous at that point. And also the limit of f of x as x approaches 2 does not equal f of 2. Let's continue on to this third example. As I draw my function, I have to pick my pencil up at -4. I also have to pick it up again at 0, and then I start again. I have to pick it up at, this looks to be 1, and then I can continue on. So in this, how many times did I wind up picking up my pen or pencil? That was 3 separate times in order to draw this function. So you can see that my points of discontinuity are x equals -4. That was this one here. Then we have x equaling 0. You can see I have what kind of asymptote? A vertical asymptote. Keep practicing using those definitions. Even though we're not on that lesson of vertical asymptotes, it's helpful to still be able to discuss it. So keep up with those definitions. And then lastly, at the point 1. So when x equals 1, I also have a point of discontinuity. Now, what makes these points of discontinuity different is that, well, let's see what this first one fails. When x is equal to -4, am I defined? No, I'm not even defined. So f of -4 is undefined. That's that first condition we look for. Then next, well, the limit exists, but since we're undefined, that limit does not equal the value of f of -4. So the second condition holds true, but that third condition does not. Now, let's look at x equals 0. F of 0 isn't even on here. It's undefined. Also, the limit doesn't exist. We're going towards positive infinity from the left and negative infinity from the right, but regardless, even if both were headed towards positive infinity, it's still infinity, so we say it doesn't exist. So we failed condition 1, we failed the second condition, and then obviously we're going to fail the third condition because of that. So just to save time, I'm going to write that it fails all conditions. And then lastly, let's look at x equaling 1. Well, f of a is defined. You can see it right there at the point 1, 2. So even though it's undefined as we're along the line, we're still technically defined at x equals 1. So check on that first condition. Second condition, well, the limit exists. As we approach 1 from the left and as we approach 1 from the right, our function approaches that same value. So the limit also exists. In this particular case, we only fail one of the above conditions, and that's that final condition. That whatever that limit is, it's going to equal the value of the function at that point, which this does not. You can see here the limit is approximately, I covered up my numbers, so let me erase that, it looks like the limit is approximately -1, whereas the function is defined at 2. So we will say in this case that the limit as x approaches 1 of our function does not equal f of 1. You can see that for our limit, we got -1. That does not equal f of 1, which has a value of 2. So that essentially is continuity at a point. We have to check all of the points in question to see if our function is continuous. But let's say we don't necessarily have a graph. Well, we know what makes a function undefined, so let's give example 2 a go and see. In example 2, we're going to state whether the function is or is not continuous. If it's not continuous, we're going to find all of those points of discontinuity. We won't have to state why in this, but we can talk about it or mention it. So we have some polynomial. Is there anything or any value that I can't plug in for x? No, with just a straight up polynomial, there's not. So this in part A is continuous. Let's zoom on into part B. In part B, what can x not be? My denominator cannot be 0. So if x minus 2 equals 0, my function's undefined. And that occurs when x equals a positive 2. So that is my point of discontinuity. Now, because we've gone over limits, especially limits that are approaching a finite value, what do you think we'll have here? Will we have a hole or will we have a vertical asymptote? Remember, a hole occurs when that factor in the denominator can be canceled out. A vertical asymptote occurs when it cannot. So when we have a hole, the limit still exists. When that factor can't be canceled out, a vertical asymptote, our limit doesn't exist. We're either heading towards positive infinity or negative infinity, or potentially both, depending on whether we're approaching from the left or right. So let's see if this cancels out just for fun. X squared plus 3x minus 10. What multiplies to give us a -10 and adds to give us 3 is x minus 2, a factor of that. This would be x plus 5 and x minus 2, because -2 times 5 gives us a -10, and 5 minus 2, or 5 plus -2, gives us a positive 3. So indeed, our factor will cancel out, so that was just a hole, and the limit technically still exists for b. I didn't ask you about this, but it's good to talk about and be prepared to do this with any function. Let's move on to part C. We have to ask ourselves, when is this function potentially undefined? Is there any points of discontinuity? If we're looking at the denominator, x squared will always be a positive number, and we're always adding to that, so we're never going to have 0 in our denominator. Therefore, this is a continuous function. And lastly, in part D, we still have that x squared in our denominator, except now we're subtracting a value. So when we get positives out of our x squared, there will be 2x values that when we subtract 4 from x squared, we're going to get 0. So what I'll do is I'll say x squared minus 4, when does that equal 0? Because that's when our function's undefined. If we add 4 to both sides, that's when x squared equals 4, which occurs when x equals either a positive or -2. If we take the square root of 4, that is a positive or a -2. -2 squared does indeed equal 4, and 2 squared does indeed equal 4. So we actually have 2 points of discontinuity for this function. We have it as x equals -2 and x equals 2. Those are 2 points of discontinuity. So if I wanted to, I could rewrite my denominator as x plus 2 times x minus 2. That is the factored form of x squared minus 4. Let's continue on to the next part of this worksheet. And in this case, we're going to talk about continuous intervals, because we understand now how to figure out a point of discontinuity and where that point of discontinuity lies. But how do we represent that the function is continuous everywhere else? That's by describing or expressing that interval of continuity. But first, we have to learn about whether our endpoints are part of that interval or not, because endpoints will play an important role in deciding if we're going to be using a parenthesis on our interval or if we will be using a bracket on our interval. A bracket means that the point is included in that interval. A parenthesis means that the point is not included in that interval. So let's look below at this picture I've drawn. Now, I didn't say one way or another whether I'm including the endpoints or not. So we're going to go through a couple different cases. If I have both of my points filled in, you can see that my interval is from -1 to 5. So how I would say this interval of continuity, because you can see that it's continuous along that entire line, I have no holes or jumps, I would say that my function is continuous from -1, note the square bracket because that point is included, to 5. Again, that last point is included. And those are x values that I'm doing this interval across. So from -1 in the x to +5 in the x. Another way you might have written this is -1 is less than or equal to x, which is less than or equal to 5. Whenever I have that less than or equal to, I have a square bracket. If it was just less than, that's when I use that parenthesis. So let's mix it up. Let's put an open circle on this endpoint when x is equal to 5. Well, -1 is still included, but now 5 is going to have an open parenthesis. All right, let's fill 5 back in, but now let's have -1 as that open circle. Well then, now -1 has the open parenthesis on its side, and 5 is enclosed in that bracket. So you would read this as -1 is less than x, which is less than or equal to 5. You can see that 5 is included in that interval where the -1 is not. And let's do one more. Let's do it to where both of them have an open circle. That would be -1 is less than x, which is less than 5. That's how we would write our interval. Now let's say that this function continues on elsewhere. If we had another interval of continuity within that same graph, we would write both of them with a u in between, meaning union. You could also write and, meaning that it's continuous on this interval and this interval, or write a comma in between those multiple intervals of continuity. It all depends on the notation that your teacher wants you to use. I personally like the u for union, meaning that it's both this interval and that interval. So when you see me write this u, just think union or think and. So let's look at these examples below, and we're going to write the intervals of continuity for each of the following. So you can see in A, I have multiple points of discontinuity, and at those points of discontinuity, that's where it's breaking up my continuous intervals. So let's start from the left of our function and work our way towards the right. So you can see that we're continuous, and I'll add arrows to the edge of this to show that our function continues on. So if that function continued on to the left, that's going towards -infinity in the x. And we'll just assume that there are no holes or breaks further down. So we're going to say -infinity, comma, if we follow along that function, we stop at what in the x? At -1 in the x, and that is indeed included in that first chunk of the interval. So we're going to go from -infinity to -1, and that bracket with the -1, because that point is filled in, is square. Now you may be asking, why did I not put a bracket on that side of -infinity? You will always use a parenthesis when dealing with -infinity or positive infinity, because remember, those are just these arbitrarily large, either negative or positive numbers. It's a concept to express that x continues on towards very large values. So now I'm going to do the u for union, and we're going to look at our next chunk. So this interval here until that next point of discontinuity, which occurs at x equals 3. Notice that when x is equal to -1, I have an open circle, meaning that -1 isn't included, and I'm continuous up until I get to 3. 3 is not included. So this next interval is -1, comma, 3, because I'm using those x values for these intervals, and it's -1 to 3, and those x's are not included in that interval. And then lastly, you can see, finally, I'm going to put my last u, so I'm going to also do the union of that, and when x is 3, my function is filled in, so that's included, and our x continues on towards infinity. You can see that arrow that I included in that diagram, our function continues on, and because our function is continuing on, x also continues on towards infinity. So then I have a bracket with my 3 because it's included, and my x does not have a stopping point, so it goes towards infinity. So there's my parenthesis. So these 3 intervals make up my entire interval of continuity. Each of these represents where my function is continuous. And if I asked you for those points of discontinuity, look, we know we're not continuous at -1, and we're not continuous at 3. So when x equals -1 or x equals 3, that's where our interval was broken up. We know that we're not continuous there. Otherwise, if we were continuous, this would just say -infinity all the way to infinity. Boom, we're continuous everywhere. But we're not. We have these breaks or holes. Now that we've done that with a graph, let's go over a couple of them with a function. Here, in part B, I grabbed h of x from up above in example 2D. So if you remember from 2D, we had how many points of discontinuity? 2. That was x equals -2 and x equals 2. Those were our only 2 points of discontinuity, so our function is continuous absolutely everywhere else. So I'm going to make a note that our discontinuity points were at x equals -2 and 2, and I'm going to be sure to break up my interval at those points. So we're going to go from -infinity up to the first discontinuity that occurs along our x-axis is -2. Then we're going to be continuous from -2 up to that next point of discontinuity, which is 2. And then from there, we're continuous on. So from 2 to infinity. Note that for this problem, I did not have any brackets because -2 and 2 are always undefined whenever I try to plug them in for my function. Unless otherwise specified, like in a piecewise function, when our function's undefined, there's that open parenthesis because it's not included. In part C, what makes our function not continuous? That's when the denominator equals 0 in the case of a rational function. So what multiplies to give me a positive 12 and adds to give me a -8? That's going to be x minus 2 and x minus 6. The -6 and -2 multiply to give me a positive 12 and add to give me a -8. So how many points of discontinuity do I have? 2, because my denominator x cannot be 2 and x cannot be 6. If it's either of those, I get 0 in my denominator and we're undefined. So at x equals 2 and x equals 6, we have points of discontinuity. So we're going to break our interval up at those 2 points because our function is continuous everywhere else. So we're going to have -infinity up to that first point of discontinuity, which is 2. And again, the order in which you go does matter for this. We're going from the lower x values to the upper x values as far as our points of discontinuity go when we write them in interval notation. So -infinity to 2, union to our next point of discontinuity, which occurs at 6, union from 6 on to infinity. That's my interval of continuity, all those x values where my function is continuous. And then lastly, we're going to continue on to part D. And in D, we have a radical function. And it's important to note here that our root is an even root. It's the square root. What can we not have under an even root? We cannot have negative values. So 16 minus x squared has to always be what? It has to always be greater than or equal to 0. We can have 0 underneath the radical, that's fine, but we can't have those negative numbers. So what I like to do here is I like to just solve this inequality through to see what kind of x values I'm allowed to have. So if I add x squared to my other side, I'll get that 16 is always greater than or equal to x squared. So from here, let's just think about this. If 16 is always greater than or equal to x squared, what squared will give me 16? That's going to be either a positive 4 or a negative 4. So if 16 is always greater than or equal to that, then I'm going to be between -4 and 4 always in order for this inequality to be true. As soon as I get bigger than those two values or outside of those two values, let's say -5, -5 squared gives me 25. 16 is not greater than or equal to 25, or even that +5 squared, or +6 squared. I'm going to be outside of those bounds. So for this, I'm only continuous between -4 and 4. Anywhere else, my function will not be continuous because I'll get a negative number within my radical. So as long as I stay between -4 and 4, my function is continuous. Now before we move on, there's lots of other types of functions as opposed to rationals, radicals, piecewise functions. There's tons of other functions where you might be asked to find that interval of continuity, like a trig function, sine or cosine. Sine and cosine are continuous for all x values if you can envision those graphs, but then think of something like tangent. Well, tangent is technically sine over cosine, so sine of x over cosine of x. That means whenever cosine of x equals 0, our tangent function's undefined. So tangent actually has a lot of vertical asymptotes. So that's where the domain of our function will come into play with the interval of continuity. Or if you think about e to the x, the inverse of that is the ln of x, right? We did that a couple videos ago. E to the x was continuous for all x values. As we approached infinity, e to the x approached infinity. As we approached -infinity in our x, e to the x approached 0. But it was still continuing on. However, when we did that ln function, as x approached infinity, the ln of x also approached infinity, but we couldn't approach -infinity because for x values that are negative, the ln function's undefined. So go ahead and take a look at those graphs and try to write the intervals of continuity for a couple other functions. Come up with some problems on your own and give it to a friend to try out. But for the sake of time, let's continue on, and I'm quickly going to introduce the intermediate value theorem. I think this is a pretty intuitive theorem based on continuity, so we'll go ahead and talk about it. The intermediate value theorem states that if f is continuous on the interval from a to b, meaning that a and b are included, you can see those square brackets, and L is in between f of a and f of b. So L is some value, let's call it a y value, that's between these other two function values, whatever f of a is and whatever f of b is. So if this is true, then there is some value c in that x, so c is somewhere in this interval from a to b, where f of c, that function at the point c, is equal to L. Now, I know this seems like a lot of words, and I just told you that this was pretty intuitive, so let's look at it on a graph. For this graph, my interval goes from 1 to 3. So here is A all the way to B. You can see from 1 to 3. Next, you can see from here that f of a, when I plug 1 in for x, I'm at 1 in the y. So f of a, or f of 1, equals 1. And then f of 3 gives me a positive 7. So what the intermediate value theorem says is that we can pick any y value or any function value between 1 and 7, then we're going to be able to find an associated x value down here that's within this interval. So in this case, I picked an L of 3, and look, sure enough, I have some value c, which is 2, where f of c equals L. F of 2 is equal to that 3. The only case where the intermediate value theorem is going to fail us is if the function is not continuous, which is the point of bringing up this intermediate value theorem in this section. If you think about a function that's not continuous, I'll do something from, let's do 1 to 3 again, but let's make 1 go up to here and then stop, and let's make a jump and then continue on with 3. And let's say that my f of a, so my f of 1 is going to be a value of 2, and f of 3, let's make that go all the way up to 8. Well, you can see in between these, I have a whole bunch of y values that don't even exist because it's not continuous. So if I try to look for some value, let's say that this is 5 right here, I'm not going to be able to find an x value in between 1 and 3 that gives me that value of 5 when I plug x into my function. However, if this was continuous, so let's go ahead and connect, you will see that I will indeed be able to find some value within that interval of 1 to 3 that gives me that L of 5. And there we go, that's a quick overview of the intermediate value theorem. And quickly, in case this question comes up, you can have a function that looks something like this, where if my interval was from here to here in the x, and I chose this value for my L, you can see that that L value occurs more than once. That's completely fine, but we're saying that there is at least one x value, one c, that's associated with that function value of L. So that pretty much wraps up this example worksheet. Hopefully from this, you can understand what makes a function continuous. And let's run through those 3 conditions that make a point along a function continuous one more time. First of all, if we choose some a value, that f of a has to be defined. Next, that the limit has to exist. So as x approaches a, the limit of f of x equals, well, it just exists. It equals some number. And then the third one is that the limit of our function as x approaches a is equivalent to f of a. So what we're defined at is the same value as what the limit equals. Essentially, as we approach that x value, we're approaching our function valued at that same exact point. And if all 3 of those conditions are not met, if at least one of them fails, well, we'll either probably have a hole or a break, meaning a point of discontinuity. So now that we've summarized this, feel free to continue on to the next video. But until then, good luck with your online learning.